All right, with how this is presented, let's go back to the part of the problem here where it says we have a gap width that varies linearly with the temperature. So we have actual application going on here between two ideas, but when we see that varies linearly idea, we need to think about how y varies linearly with x. So if y is going to vary linearly with x, and I want to designate some variables here, setting up an ordered pair to represent how these ideas are going to be compared, my temperature would have to be the x idea, so I'll let T stand for temperature. My width would be the y idea, so I'll let W represent the width. If I'm trying to write a particular equation for this width in terms of the temperature, now let's set up our points here. Let's set up a couple of ordered pairs here to figure out what that equation is going to be. Well, looking back at the values they gave us, it says suppose a bridge has a gap of 1.3 centimeters when the temperature is 22 degrees Celsius. If I set up an ordered pair based on those two values, the temperature, T, would be 22. The width, W, would be 1.3. There's an ordered pair to represent that scenario. The rest of the values they give us here, it says the gap narrows to 0.9 centimeters when the temperature warms to 30 degrees Celsius. Okay, other ordered pair. Temperature, T, would be 30 here. And that width, W, would be 0.9. So if the question was, write a linear equation, some line goes through these 2 points that are given, we could do that because we could find, first of all, the slope of the line that contains those 2 points. So let's look at that first. If I want to find the slope, just subtracting between the points my y's, I could take 1.3 minus 0.9, and then subtracting with my x's, being consistent with the points here going first to second, it'd be 22 minus 30. If you calculate that slope out, well, let's see here. 1.3 minus 0.9, you're going to get 0.4, right? Over 22 minus 30, you're going to get negative 8. Okay, we can do a little bit better than that. We could actually, well, we could simplify the fraction, or if you want to divide it out, we could divide it out and come up with a decimal here. Either way, if we divide it out, what kind of decimal did we get here? No, it's going to be negative. Alright, so if we stick with the decimal value, get negative 0.05 back. Once we have our slope, well, we can set up our equation for this situation, our linear equation for this situation. If I use point slope form, I'm going to take y minus, in this case it's going to be w minus, to be consistent with my variables. W minus, select one of the 2 points to work with, doesn't matter. I'm going to select the second one. W minus 0.9. That's going to equal, continuing with the point slope form, my slope, which is negative 0.05, times, well, the rest of this would be x minus, so x here is represented by temperature, T. T minus, the point I was working with was the second one, so it's going to be T minus 30. Now, as equations of lines go, that's okay. But we do want to write an equation that basically is representing a function here for a width in terms of a temperature. So it would make sense to solve this for W, because W would then equal everything in terms of T. So solving for W, W is going to equal, I'm going to add my 0.9 over. Now, while I add that over, I'm going to distribute through the negative 0.05. So it's going to be negative 0.05 T. And then negative 0.05 times negative 30, that's going to be plus 1.5 there. We're adding over the 0.9. Clean this up a little bit more, collect some like terms. And our like terms go together. We're tacking on a 2.4, right? I would say that's a suitable equation. It represents a function here for the gap width compared to the temperature. Okay, well, once we have an equation in place, it'd be nice to use it for something. So let's go down to some of these follow-up questions. For part B, we're trying to figure out how wide the gap would be at 35 degrees Celsius and then at negative 10 degrees Celsius. So thinking about what 35 degrees Celsius and negative 10 degrees Celsius represents in the context of this question, obviously those are temperatures, so those are going to be associated with our t variable. We could go back to our equation up here that we just found, substitute 35 in for t, then substitute negative 10 in for t. That would give us those widths that we're looking for. So if I do that substitution, let me start with 35. Since I'm looking at this in the context of a function, I'm going to say w, and to show what I'm plugging in, I'm going to say w of 35. When 35 gets plugged in to this equation, we've got negative 0.05 times 35 plus 2.4. At the same time, I could do some substitution here with negative 10, set up what I need to calculate to find the gap width at negative 10 degrees Celsius. It'd be w of negative 10 equals negative 0.05 times negative 10 plus 2.4. So we calculate those two ideas out, get our gap widths. Got our values back for each. This is an application, so we think about what the gap width represents. It's a width that's represented in terms of centimeters, right? So it'd be 0.65 centimeters up here when the temperature is 35. It'd be 2.9 centimeters here when it's negative 10, when the temperature is negative 10. All right, so part C here. Next follow-up question. At what temperature would the gap close completely? All right, so we're talking about the width, right? W. If it's going to close completely, what's W going to equal? 0. So if I go back and take this equation that I set up in part A, let my width be 0. 0 is going to equal negative 0.05 T plus 2.4. Solving for T, my temperature here, subtract the 2.4 over. That equals negative 0.05 T. Divide both sides by that negative 0.05. Temperature is going to come out to be, when you do that calculation, let's see, I ended up with 48 degrees Celsius. So that would be the temperature when the gap is closed completely. Now, what mathematical name is going to be given to this temperature? Any ideas? And since X has that meaning of temperature, this would be known as the temperature intercept. Alright, so if we're sticking to the theme now of intercepts, since we introduced that in part C, part D says what is the width intercept? What does this tell you in the real world? Well, the width intercept is going to be when the temperature equals 0. And when the temperature equals 0, you go back, relate to your equation up here, temperature becomes 0. What's left over Well, the width intercept that's going to be left over is just going to be the 2.4. And that kind of makes sense too when you think about this being in kind of a slope-intercept form, right? This is like my y-intercept idea over here, and y connects to the width in this case. So it's 2.4 as far as units of measurement are concerned, centimeters. But what do you think this tells you in the real world? This is going to represent your gap width at the freezing point. Right, it's the gap width at the freezing point because we're at 0 degrees Celsius.